Hi all, today I'll be talking about this new result, which is fast list decoding of univariate multiplicity and folded Solomon codes. This work was done jointly with my amazing collaborators and mentors at TIFR, the Prahladh Harsha, Mrinal Kumar, and Ashutosh Shankar. The slides I use here are due to Mrinal and Ashutosh, and I have done some tinkering and I've made some edits and possibly induced some errors. And like any errors here, any missing citations, everything is due to me. So let's begin. So our main result is that for univariate multiplicity codes and folded Reed-Solomon codes, we give a nearly linear time algorithm, that is n polylog n, that list decodes up to the list decoding capacity. So we have a few minor caveats, which is we require the rate to be constant, and we require the characteristic of the field to be large or 0. So these are minor assumptions, and under these we have our result. So let's try to understand what the result is saying. So what is the problem of list decoding? So you have a code which is a collection of strings which are spaced at least delta apart in Hamming distance. So now there will be at most one code word within a delta by 2 radius of a corrupted received word. So the unique decoding problem is to just find this word. So even in a slightly larger radius, there will be only polynomially many code words. If you just increase the radius by a little bit, you shouldn't expect to have a lot more suddenly exponentially many code words. So the list decoding problem is to find all of them. The largest possible radius for which the list is polynomial sized is called the capacity and is around 1 minus the rate. So you could think about it for like the codes we will talk about, like 1 minus rate will be around the distance itself. So good. So what are the quantities for which we know that there are small lists? So here there's a nice result due to Johnson. This is called the Johnson radius that says that for any code C with distance delta and alphabet size q, and for radius less than this Johnson radius, the list size is always polynomial in n and q. So here j, q, comma delta does not depend on anything else about the code except just the alphabet size and delta. So this is some quantity. So for our codes where like we'll have large q and our codes will meet the singleton bound, i.e. r plus delta is around 1, we'll have that jq comma delta is 1 minus root r. This is because 1 minus 1 by q will be approximately 1 for us. Again, q by q minus 1 will be approximately 1 for us. And then 1 minus delta is just r. So this whole quantity turns out to be about 1 minus root r for us. Good. So what we know is that for our codes that there are r small lists whenever radius is less than 1 minus root r. Now the question is, can you find them? So for this question, we first consider our most natural and our favorite family of codes called the Reed-Solomon code. So the Reed-Solomon code comes again with the 3 parameters. One is q, n, and d, and a set of evaluation points which I have not included here but are also ideally part of the parameters. So what it takes is take all polynomials f which have degree less than d and evaluate them on alpha 1, alpha 2, all the way up to alpha n. So observe that there are about q to the d polynomials and q to the so the rate of this code is just d by n, because if you take log base q, this is d and then n, and the distance can be checked to be 1 minus d minus 1. Johnson radius, as a reminder, it will be about 1 minus root r for us. So the question is, can you list decode up to the Johnson radius? And let's see. So what are the results here? Unique decoding, of course, we have known for a long time due to some amazing algorithms by Berlekamp-Welch, Berlekamp-Massey, and Peterson, and so on. But we also know that you can actually list decode up to Johnson radius. This is due to some amazing work in the late 90s by Sudhan and Guruswamy Sudhan. So Eleknovich in 2002 also showed that Guruswamy Sudhan can actually be implemented in near linear time. So this is like similar parameters to us, like n polylog. So the question is, this is still 1 minus root r. Can you do beyond 1 minus root r? Can you construct explicit families of code for which you can decode beyond 1 minus root r? So there were several breakthroughs in the early 2000s. which showed that you can actually construct explicit codes that can be coded beyond the Johnson radius and all the way up to capacity, in fact. So this was due to Parveshwadi. We had Parveshwadi codes in 2005, then folded Reed-Solomon codes due to Guruswami Rudra, and univariate multiplicity codes due to Guruswami Wang and Koparty. And all these families of codes were shown to be efficiently list decodable up to capacity. So let's see one of the families of codes. In particular, let's look at univariate multiplicity codes. So U mult of Q and comma D comma S. This is again the similar parameters as the Reed-Solomon code with this one extra parameter S, which is the multiplicity parameter. So this again here, similar to Reed-Solomon code, this might look scarier, but it's just saying that now in each bit, instead of just giving one polynomial evaluation, you also give its derivatives evaluation, your derivative of derivatives evaluation, all the way up to S minus 1 derivative evaluations. So this is a clean generalization of Reed-Solomon code. So Reed-Solomon codes are just S equal to 1 here. Good. So what do we know about list decoding for univariate multiplicity codes? Okay, just as a quick note, let's observe that the rate here is d by Sn, and the distance is 1 minus r, again, roughly for us. Good. So list decoding of univariate multiplicity codes. So Koparty and Guruswami Wang showed that univariate multiplicity codes with parameter S, the multiplicity parameter, if the multiplicity parameter is greater than 1 by epsilon square, roughly, you can list decode efficiently up to 1 minus r minus epsilon. Here I'm thinking of epsilon as a constant always. Guruswami Rudra showed the same result almost for folded Reed-Solomon codes. So the natural question we ask is, can you do an Elefnovich style argument and run all these, like any of these algorithms in near linear time and list decode folded Reed-Solomon codes or univariate multiplicity codes up to capacity? So the question has been could have been asked 13 years ago, you would say, but it wasn't as clear back then that this is a valid question to ask, because the list sizes in Guruswami, Wang, and Koparty are around n to the order 1 over epsilon, and you need to output the list. And if you output the list, you have to spend at least the size of the list amount of time. So it's not immediately clear that this question makes sense. But due to some amazing breakthroughs by Koparty, Ronzi, Saraf, and Wouters in 2018, they gave a randomized algorithm to prune the list down to constant size. So they in fact showed that the list, even if like you find it to be n to the order 1 over epsilon, the actual list is actually constant. Here a constant is some not so nice dependence in epsilon, but it's just a dependence in epsilon and no dependence in n. So KRSW18 can run in near linear time given a Guruswami Wang style description of an affine space where all the close code words lie. So now our goal will just be to find a near linear time algorithm to find a Guruswami Wang style description of an affine space where all the close code words lie. And we show that indeed you can do this. There is an algorithm to run Guruswami Wang and find this affine space in near linear time. Good. So let's look at what our result is again and remind ourselves. So we show that for univariate multiplicity and folded Reed-Solomon codes, there is in fact a near linear time algorithm that list decodes up to list decoding capacity. And a main new ingredient, building upon Elefnovich's work, Guruswami Wang, and so on, is this fast linear differential equation solver. So what it says, if you have some a of x, a naught of x, all the way up to a of x, which are all polynomials of degree less than n, let's say, find all f, again, polynomials of degree less than n, such that a of x plus a naught of x plus into f of x and so on. And this resulting differential equation is identically zero. And we want that we show that this algorithm, the differential equation solver we have, runs in time n polylog n. It has a polynomial dependence in m, but m for me will always be a constant, so it's okay. But and some polylog dependence in the field size as well. So let's see how Guruswami-Wang works. So Guruswami-Wang has two major steps. The first step is called the interpolation step. They construct a multivariate polynomial, which is like an explanation polynomial, such that q of x1, these y variables, it's linear in the y variables, and it's polynomially dependent in x variables. So you could think of it as it's a linear polynomial in y1, y2, yn, and with coefficients coming from polynomials in x. So if what this will end up working as, like, if there is any r of x which is received to the closed code word evaluations, then instead of y1 if I plug in r of x, instead of y2 if I plug in the derivative of r of x, and so on, this resulting polynomial, which is now just a polynomial in x, would be identically zero. So you would want u of this form somehow. So this is done by setting up and solving a system of linear equations, and you show that you can find such a q, there exists such a q because you'll have more variables and constraints and so on and so forth. It's a very clever and very beautiful argument. But yeah, this is the first step. So it's important to note that this can be done, but it will not be near linear because they will need to solve a system of linear equations, and that will require at least quadratic time by standard methods. Good. So what's step two? When you have a differential equation, solve it. Find all r of x which are close to it. Good. So these are the two main steps, and this is efficient and decodes up to capacity. But the important thing to note is, like, this is not linear time, near linear time. This is absolutely beautiful work, though, and we just build upon it and just run this faster. But yeah. So what is our improvement? We need to speed up both steps. So the first step is very similar to Aleknovich, and it's just like Aleknovich speeds up Goswami-Sudan, and we follow basically Aleknovich's ideas and simulate them, and with slight tinkering, we can show that they can actually be made to work with Goswami-Wang as well. Now the second step, speed up, is slightly trickier. So for Aleknovich, the final problem that needed to be solved fast was a factoring problem in Guruswami-Sudan. And for that, there was already existing, again, beautiful literature that showed that you can do that. For us, the problem here is a fast solver of differential equations of this form. Again, this is just the same form that I'd flashed to you a few slides ago. So let's focus on this step to speed up and see how that happens. So this is the structure, and here it can be shown that the degree, like the space of all solutions, forms a dimension, a fine subspace of dimension at most m, and we want to find a basis for the subspace. So the simpler case to consider is when a0 of x plus a1 of x into r of x is 0. So this is like the case when m is equal to 1. So I'm just like no derivatives for now. Sorry, this should be m equal to 0, but yeah. So here the obvious solution is long division. Just divide a1 and a0. But we want near linear time. And so let's look at a very nice idea. So this idea is you can write any r of x that works as, instead of a degree d polynomial, as two polynomials, u of x plus x to the d by 2 v of x. And u and v will be at most degree d by 2. So now you have a condition of this form, which is a0 plus a1 0 plus x to the d by 2 into a1 v is 0. For this, firstly we need, if you look at this condition mod x to the d by 2, this a1v term disappears because it's multiplied by x to the d by 2, and you get that just a0 plus a1 0 is 0 mod x to the d by 2. So now you can solve for u, which is, again, now this is a d by 2 degree instance of it instead of a degree d instance. Once you have found such a u, you try to find v. Now you have a condition which is mod x to the d, But you have that b is a naught plus a1u, and that is already divisible by x to the d by 2. So you can remove the x to the d by 2, and you'll get another different condition, which is also degree d by 2. So now you'll have two smaller problems, which are both d by 2. So you'll have something of the form that the time you need to run for d is 2 times the time you need for d by 2 solutions plus some linear processing time. And we know that this would result in a near linear algorithm. So good. Then we are done with m equal to 1. But now what about higher multiplicities? What about higher m? So the main problem that first happens is the solutions are no longer unique. So you can't branch because you'll have more solutions and more solutions and more solutions, and it's not good. So that it's important to remember that we had this affine space and we just want to find a basis for it. So we'll fix the base. We'll find a basic for each basis vector. We'll find a differential equation and find its unique solution. So for each basis vector, there'll be a unique solution, and you can show that there is a version of divide and conquer that actually works here. So let me close with some remarks and open questions. So our algorithm, roughly with like slight modifications, also works for folded read Solomon codes. And there are some natural open questions, which are: do we have good generalization to multivariate polynomials? What about list decoding for multivariate polynomials? In general, it would be nice to have a better understanding of standard Reed-Solomon decoding beyond the Johnson bound. And just what about when evaluation sets have small lists? What evaluation sets have small lists, etc. And just it would be nice to see some more algorithms. So in summary, we have a near linear time decoding of univariate multiplicity codes via fast differential equation solver, and we can also do something similar for folded Reed-Solomon codes. Thank you. I will close here, and again, I would like to also recognize my collaborators and thank them for their work, which is Prahladh, Mrinal, and Ashutosh. They're amazing.